Welcome to Chapter 9, Part 2. In this last section of the chapter, we consider rocket propulsion as purely due to conservation of momentum. However, in this special case, we must take into account that the mass of a rocket is not constant, since much of it is in the form of fuel, rocket fuel, which is spent as the rocket propels forward. So let's see if we can work through and understand conservation of momentum and rocket propulsion. First, we begin by setting the variables. Initially, we have capital M, which is the mass of the rocket, plus delta M, which is the mass of the rocket fuel. V is the speed of the rocket relative to Earth. After a time increment delta t, the rocket will eject fuel of mass delta m and as a result speed up. So the corresponding speed increase of the rocket is v plus delta v. Vex is the speed of the exhaust gases relative to the rocket, and v minus vex is the speed of the exhaust gases relative to the Earth. All right, well, let's consider conservation of momentum. The initial momentum of the rocket is its mass times its velocity. The final momentum of the rocket is its mass times the increase in its velocity plus the amount of fuel rocket times its speed relative to the Earth. If we now multiply these out, we see that mass of rocket times speed plus mass of fuel times speed equals mass of rocket times speed plus mass of rocket times increase in speed plus mass of rocket fuel times speed of rocket relative to the Earth minus mass of fuel times the speed of the fuel relative to the rocket. We can see that this term and this term cancels out. We deduct it from both sides. This term and this term cancels out. So effectively we have the surviving terms mass of the rocket times the increase in the speed of the rocket minus mass of the fuel times its speed of exit from the rocket. And so we rearrange the terms to come up with this expression. So conservation of momentum relates the mass of the rocket times its increase in speed to the mass of the fuel times its exhaust gas speed. Now, of course, if we now take the case in which we consider the instantaneous value, in other words, the value of the changes in speed at every instant in time, we allow delta t to equal 0 so that we are at an instant in time. The mass of the rocket fuel, delta m, we are now going to write as the loss in the mass of the rocket minus dm. So we have this expression here from this expression, and we rearrange the terms so that after we integrate both sides, we have the change in speed, delta v, the change in speed of the rocket from its initial to any point thereafter is equal to the escape velocity of the gases, the exhaust gases, times the logarithm of the ratio of initial mass to final mass. from Newton's second law, we can write thrust. Remember, thrust is a force. It's the force at which the rocket thrusts forward as the mass of the rocket times its change in velocity with respect to time. And its change in velocity with respect to time, as you can see here, is nothing more than this expression right here, where m dv over dt is, if we put a dt on both sides over here, dv over dt, it's entirely equivalent to dm over dt times v of the exhaust gases. And so this becomes an expression for calculating the thrust of the rocket in terms of the rate at which the mass of the rocket changes as the fuel is spent. Now let's watch a video.
To rocket their way into Earth orbit, space shuttle astronauts rely on the principle of momentum conservation. The roar at takeoff is created by the high-velocity gas that the engines eject out the back of the spacecraft. This gas carries a large momentum, and by the principle of conservation of momentum, is balanced by a forward thrust large enough to accelerate the massive rocket toward Earth orbit. During the ascent, the solid rocket engines are ejected with an explosive charge. This explosion creates internal forces that are shared among the shuttle, the external fuel tank, and the booster rockets. Because these forces are all internal, the explosion cannot alter the motion of the center of mass. Shuttle astronauts also use the principle of momentum conservation to maneuver the vehicle in orbit by firing small thruster jets that eject gas at a high velocity.
So as you can see, conservation of momentum is responsible for rocket propulsion. We can explain it. By the way, the mention in the video about the internal forces, although we haven't studied center of mass yet, what they're guaranteeing us is that because all the forces are internal by Newton's third law, any one object exerts the same force on the other. There's no external force, and therefore we are correct in assuming conservation of momentum. This concludes part 2 of chapter 9. Until next time.